I'm recording, but there's nothing there. Are we there? Recording. Check, check, check. All right. Bone functions. This is where we left off on your study guide. It is going, right? Yeah. Good, thank you. We left off here, right? We had gone through our homeostasis and bone development. And again, if you weren't here, the recording is up online. Make sure you check it out. There are these little questions, right? I've almost given you what would be like a test question, right? A little short answer of how you should be able to explain how the bone grows, how that homeostasis works, etc. All right? So be comfortable with those pieces. Bone functions are what we want to spend some time talking about here today. And then we'll roll into the last little bits about joints. Those are the two pieces we really haven't covered yet. Yes? We did. At the very end of the last class period, what I would push you toward is there's one paragraph on page 148 that explains it very nicely. It's very much just about the osteoclasts and the osteoblasts. There is one little paragraph that says homeostasis of bone tissue on page 148 about the reabsorption and the deposition. So osteoblasts putting down bone, osteoclasts breaking down that bone. Because we need the minerals for your body to work, and you're storing them with the osteoblasts. So it's this homeostasis, right? Everything goes back to homeostasis. If that gets out of whack, the bones either get super duper thick, which is a problem, or they get super duper thin, which is a problem, right? No, it's better to be homeostasis. No, I would choose neither. Yeah, no, they're both a problem, truthfully. Even if they're thicker, they still will break easier. Yeah, they still will. Right? It doesn't mean you're like just over-engineered. Just again, the structure is enough that it just doesn't work well. So let's talk about these different functions. So your textbook puts these two together, support and protection. I separate them because those are kind of two separate things in my mind. What do we mean by support? Sorry? Okay, like literally holding up, right? So I'm holding in the organs. Okay. What else? So I can stand, right? I'm not just a blob of mess on the ground, right? Because skin is just, it's almost like a liquid, it's shapeless. Absolutely, right? It gives you form, it gives you structure, it gives you support, right? So that's one main function of this skeletal system. Okay, what do we mean about protection then? Okay, protecting your organs. So what bones in particular are very much focused on protection? Give me some raised hands. What? Yes, ma'am. Skull, huge one, right? Because this thing inside here is super duper valuable. You want to have some fun sometimes. Calculate how valuable your brain is based upon how much your parents have paid for your education so far. It's pretty interesting. Wait till you finish college as well, right? Like this baby right here, this has got to be worth about $400,000, $500,000 right now. Take care of it, right? Well, I love you more than he does, I guess. So I would say you're worth more than that. Not sure. Okay, what else, Andrew? Your ribs, huge one, right? He stole yours. Man, Andrew. Yeah, the ribs, huge, right? Because again, some of your most valuable internal organs are right here, right? Heart, lungs. Intestines, not as much, right? But certainly. What else, sir? Sorry? Your pelvis, good, yeah. Nice, nice. Of course, it's kind of open in the front, but yeah, certainly. Teeth. Okay. What do you mean by that? Give me more. How would that be protection? Like if you didn't have teeth. Oh, right, cool. I never thought of that, Don, but I like it. I like it. Yes, ma'am. Shoulder blades. Sure, they're kind of giving you some protection on the back from that joint. I like it. You guys got some good thoughts. What's that? Are there some major ones? No. You got the big ones. Yeah, head, ribs, sternum. Oops, I just pushed the... Don't forget that sternum. Which one is more important, like the brain or the heart? Yes. Yes, both. That's right. You can't live with either of them, without either of them. Yeah. Okay, let's move on. I guess theoretically you could say that parts of your heart would be more important than parts of your brain, because if your heart stops beating, like, it's pretty tough to keep going. Yeah. But same with your brain. If your brain's not working, you won't live either. Yeah. Okay, body movement is another big function. And this is where we get to have a little bit of physics class. That bones act as levers or levers, depending on what country you're from. And they do that in order to make you move. The classic example is the bicep. I wore this short sleeve shirt today to show off. No, I'm just kidding. Right? Your biceps, right? So you have what we call an origin up here on the shoulder, and it inserts down here at the elbow. And again, how muscles work is they contract, they shorten, right? And when they shorten, they're bringing the insertion towards the origin. So therefore, we do this motion, this bending the elbow motion. What do we call that? Does anyone know the name of that motion? It's not extension. It's opposite of that. This motion is flexion. Again, we'll get to these in the muscle chapter. Next chapter, we'll talk about this. It's listed here in your chapter 7. But this flexion motion, okay? And so these bones basically provide the levers. They provide the places for the muscles to pull on. Have you ever seen these guys that are like super duper ripped, right? These big, huge, muscular guys, like me, but a little bit bigger, right? Joking. And there are times when they work these muscles so strong, they can literally break the bones in their wrist, in their arm, trying to pull something up. Really? They can. Often they'll actually just rip the muscle right off, which, yeah, it's You see these pictures, and there's like literally bumps. Like it's really small, and it bumps up where the muscle is literally torn away and is in this tight little ball. It's not fun. Okay? Does that make sense, friends? So the point of these levers is there's a thing in physics called mechanical advantage. You can actually move more mass with your arm working as a lever rather than just simply lifting it up. That lever helps you move more. Again, it's called mechanical advantage. It gives you a way of multiplying the force that your muscles can create based upon these levers, right? If I'm going to pick up something that's really heavy, do I do this? Like if I come to this table, do I extend my arms all the way straight and try and lift? No way. What do? I bend them a little bit, right? I'm setting up in a way that allows those levers to work. Does that make sense? Oh, sure, right, because we're not just using my biceps, certainly. You're correct. But if we're talking about just biceps, yes, certainly. All right, so support, protection, body movement, right? What's our fourth one? Blood cell formation. Okay? And there's a fancy name for that because everything in medicine has a fancy name. Hematopoiesis, the making of blood vessels. Okay, that's all that means. That starts off even while you're a baby in the yolk sac. Did you know that we have a yolk sac? Like, we'll talk about this in that chapter. That just like a chicken has a yolk, right? So do we initially, right? And inside the marrow, inside that medullary cavity of the long bones, right, you have these two kinds of marrow, red marrow and yellow marrow. The red marrow helps to make what? Blood cells, right? And there are lots of kinds of blood cells. We have red blood cells, we have white blood cells, we have platelets. So what do red blood cells do? Carry oxygen to your body, right, through the hemoglobin. What do white blood cells do? They fight bacteria, right? These are the defenders, the soldiers, right? How about platelets? Good, but in particular do something to the cut. You're correct. Before the scab, a clot. These are the clotting pieces that help, and again, it's a whole humongously long process, and we'll talk more about it, but the platelets are the big clotting piece that when you cut yourself, it helps to contain that flow and not let you bleed to death simply because you got a paper cut. Are you with me? And those are found, again, in that spongy bone area, and in particular, they tell you it's in the skull, the ribs, the sternum, the clavicles, the vertebrae, and the pelvis. These are places where your red marrow is more prominent. And the yellow marrow, what does that do? Stores fat. So if you remember that picture at the beginning of the long bone, the one you're supposed to know, it doesn't show you red marrow, right? It just shows yellow marrow. Because these long bones mostly have the yellow marrow in it, not the red. The red are located more in those specific areas: skull, ribs, sternum, clavicle, vertebrae, pelvis. Are we cool? It doesn't mean that you're like overweight and you got to lose the fat in your bones. No, don't worry about that. Again, you need. Fat is just stored energy, right? We need some of that. Otherwise, if we didn't eat, for whatever reason, we wouldn't be able to do something.
Is it harder, like, if somebody's burning fat, you just burn it like outside of the bone first?
Yeah, that's not really an easy place to access for the body. It's much easier to access other places, so sure. Yeah, certainly. We're good here? All right, next we're on to the last of the main functions is the storage of these inorganic salts. And if you remember back to our chemistry chapter, we talked about organic versus inorganic molecules. This is what we're talking about, right? So, calcium phosphate, right? This is where your bone is storing the calcium that we eat. And we need that for many different metabolic processes. So it's a very important mineral that we have to have access to. And again, the bones are that reservoir where the calcium is stored. You all know a reservoir, right? Like the reservoir I drive over every morning coming up here, right? Reservoir High School, right? That's this body of water that's like a reserve of water. And it's made because of the dam, right? The dam backs it up and you fill up this reservoir. What they're saying is, hey, we're going to keep this calcium here because who knows when the next time is that Daisy's going to eat all that calcium, right? So let's hold on to it in our bones, and that way when she needs it, we can pull it out and use it. Make sense? There's a nice little homeostasis diagram on page 152. I don't think it's here in my notes, if I'm remembering correctly. Oh, no, it is. There it is. That's showing you this homeostasis process, right? That we want to keep the blood calcium level at a certain level. Well, if it gets too high, the body will take the calcium from the blood and put it in the bones. If it gets too low, we'll take the calcium from the bones and put it back in the blood. Does this make sense? And what governs that is your thyroid gland. It releases a hormone, again, called calcitonin, that will tell you, hey, we need more calcium, or no, put it back in the bones. It regulates that piece. Yes, ma'am? Again, all these are up on Schoology, so I think I was here and actually got to the next piece. All right? We just talked about this, the calcitonin. What else does the bone store? Magnesium, sodium, potassium, carbonate ions. This was the answer to question, what was that, 35, I think it was? On your, not 35, that's the very end. 12, thank you. Yeah, that we just talked about when we went through your questions. Okay, sir?
On the previous slide, number 1, can you explain that?
They're basically telling you that calcium is stored as calcium phosphate. So it's not just calcium all by itself. It's been bonded to a phosphate ion, a PO4 ion. Because you want it to be stable. Calcium by itself would like react in your body. It would not be fun.
What's
Inorganic matrix. So we're talking about the actual bone itself. That's what they're meaning by that. The matrix just means how things are put together. Inorganic means not carbon-based. Yeah, the bone stores. The actual, like the substance of the bone stores it. Ryan, you have a question or you're just stretching? All right, good. Just making sure. Okay. Are you comfortable that your bones can also store elements that are not helpful for you? Right? If you're exposed to some of these things like lead or radium or strontium, this is why lead-based paint is such a problem, right? Little kid is, gnawing on the wall or on a crib thing that is painted with lead paint, right? That absorbs into the body takes it and stores it because it thinks it's just like any of these other things it's supposed to be storing, right? And that can lead to some developmental problems from those lead poisoning, right? That's just one example. But the same thing would happen with radium or strontium. These are radioactive pieces that would cause issues. Are you with me, friends? What's interesting about the rest of this chapter, and really we're going to ignore a whole bunch of the slides that are present here as well as in the chapter. Like they literally take you through each bone in the body, right? That's why I wanted you to do those questions, because it does roll you through all of the bones, right? And again, this is a diagram you should be comfortable with, right? Because I may not actually give you this particular diagram, but you should be able to say, hey, this bone right here is what? Humerus, good. And this bone right here is the femur, good. And this bone right here is the sternum, right? These are just easy peasy things that you should be comfortable with. Easy points, right? Good, good. Axial is talking about all the orange bones, right? In the axis of the body, like what you spin around. Whereas the appendicular are the appendages, the things attached onto there. Okay, I got to skip forward a good ways here to find where our joints are. So give me a moment to move. Pelvis. By the way, I hate the fact that your textbook calls this the hip bones. No one ever calls it the hip bones. It's the pelvis. Yeah, or the actual three names. Your pelvis is actually made of three bones: the ilium, the pubis, and the ischium, that are together on one side. Yeah. Yes. The coxal. Yeah, that is an old Latin term that's talking about hips, like the area of the hips. I can't say I've heard it called that too much. Maybe, but in an old school manual you might see that. Yeah. Almost there. Joints. Here we go. All right, and again, on your study guide, we're here, just so you know, are different types of joints: fibrous, cartilaginous, and synovial. Okay, what is a joint? Let's start with that. It's where, sir? Okay, it enables movements. I agree with that. It's kind of a function of it. But even more fundamentally, what is a joint? Where two bones meet, come together, right? So the meeting between, because actually all joints don't have motion. Some of them do. Most of them do, but not all of them. Okay? And we classify the joints based upon how much movement they have. The ones that have tons of movement, what do we call those joints? Like your shoulder, your hip. Those are synovial. And the main joints you think of are synovial joints. But we have these other kinds of joints as well. The first one is a fibrous joint. The fibrous joints are like the ones between the different bones of the skull: the frontal bone, the temporal bone, the occipital bone, the parietal bones, the lacrimal bones. These are all terms that you would have learned if we spent more time there. Okay? Those are immovable for the most part. They don't move at all. Or they might have just slight bit of movement. So between your tibia and fibula, there is actually a joint. Those two bones meet at the very bottom here by your ankle. And there's a little bit of movement that happens there, but very little. Okay? Has anybody ever heard of a high ankle sprain? They say this on football: oh, he has a high ankle sprain. That's what they mean. That actual joint between the tibia and the fibula has been stretched. Okay? And they show you a lovely picture, zoomed in. The bones come together. Remember, initially, as a baby, there is some movement there, so that way the head can rearrange its shape as it travels through the birth canal. But very quickly, those joints fuse together. This is why if you were to get into a car accident, have a head injury, and your brain starts to swell, which does happen, do you know what they do to you? They literally drill a hole in your head. A hole in your head. I can't remember what it's called. I can't remember. And what's the point of that? To let this pressure, this fluid leak out. Why? Because the bones can't expand. Right? If you mess up your elbow, it'll swell up, right? You can get this big, huge swelling in your elbow, and that's not going to kill you. But if you have pressure swelling in your head without having a place for it to be released, you could die. Because it's actually going to kill the tissue in your brain. Okay. I've not heard that, but yeah, I like that. The next piece is what we call the cartilaginous joints. So, fibrous joints, which is like connective tissue, right? Think back to our tissues. These are cartilaginous tissues. And these are ones where hyaline cartilage or fibrocartilage put these two bones together. So if you were to think about these discs in between the vertebrae, right? Those would be cartilaginous joints, right? And they help to absorb the shock of your spine up and down. This is a very up and down motion. It contains that, right? Other examples of that would be your pubic symphysis, right here between the two pelvis pieces, right? And that's, again, a cartilaginous, a fibrous joint that holds that together. The last would be up here between the ribs here and the sternum. Remember that these pieces here are all cartilage, right? They're not actually bone. So those would be cartilaginous joints. No, sure. They're just giving you particulars. But yes, here. Oh, it can heal just like the others. It would put down a scar tissue. Yeah. It would heal. Let's keep going here. Last but not least, we have synovial joints. And the synovial, what that means is you actually have fluid that encapsulates that joint. So here's a picture of one of your fingers, right? Two phalanges on either side, and you have space in between them. The white part is what we call articular cartilage, right? Remember where the two bones are meeting? You have that extra area that gives protection for the friction. That's what the cartilage is. And then notice around there you have this blue stuff. That's the fluid, the synovial fluid inside that synovial joint. Does that make sense? Synovial means there's a little sack of fluid there that helps keep it lubricated as it's moving. Because these guys move a lot. Synovial joints are the ones, when you think of joints, that's what you think of. Lots of movement. Okay? Here is another piece that's talking about, we tied this as one of the diagrams on your list. That is the knee, absolutely. Has the bursa. Remember those are little sacks that provide the friction pads as tendons or bones are moving. And we can take these synovial joints and we can classify them even more. Yes, ma'am? Synovial joints are fluid-filled, and these are the ones that have the most motion. The most motion. And again, this is on page 175. They give you the list. On page 176 is a great diagrams of all the different types of synovial joints. Ball and socket joints are like your shoulder, right? Here is the ball, right? On the end, here is the socket. And those guys move together. Your hip is another great one. The head of the femur is the ball. The acetabulum is the socket, and it moves. Okay? And those that give you large ranges of motion. A condyloid joint is very elliptical. It has this little condyle that's kind of oval-shaped that permits some different motions. So between a metacarpal, which would be here in your wrist, right? Actually, your palm are the metacarpals, and a phalange. So kind of these joints right here at the beginning of your fingers. would be an example of a condyloid. A condyle is a piece sticking out. That was in your lab, right? The gliding joints, where they're pretty much flat, and so they allow just some back and forth movement. So the vertebrae are an example of that there is some gliding that happens there, where they can move back and forth. Your wrist and ankles to allow this motion of flexion and extension, bending and extending your wrist. Those would be examples of gliding joints. A hinge joint, you've got a convex and a concave, that they fit together. So your elbow is a perfect example of that. Think about that hook, right? The end of the olecranon, right? End of your ulna that goes into this little concave piece of your humerus. And that would just move back and forth to give you your elbow flexion and extension. And last but not least, this pivot joint. Oops, sorry, there's one more after that. The pivot joint, a ring of bone, a cylindrical surface within a ring. So that would be your radius, that nice circular radius that allows for movement like this, that pronation and supination of your wrist. And like I said, there's a great diagrams that are there on page 176. Give me one moment, please. Last but not least, that saddle joint. A saddle, right? It looks like a saddle. And that's the only one that is really in your thumb. This joint right here and right here that help give you this movement, kind of a two different way movement, back and forth, up and down. Well done, friends. See you tomorrow.